In this video, we'll demonstrate how Elastifile enables enterprises to lift, shift, and go with multi-cloud architectures that enable cross-cloud workflow mobility. Here you can see the full multi-cloud architecture that we'll be leveraging in this demo. To illustrate how Elastifile delivers true hybrid cloud workflow mobility, we're going to demonstrate the seamless dynamic movement of a genomics workflow from on-premises to cloud and then between clouds. First, we're going to demonstrate Elastifile support for on-premises data processing. The workload will be the genomics workflow supplied by the Genomic Analysis Toolkit. Here we're showing the necessary files and genomic data are already available within our local file system. Now we'll run our script, which in this case is going to clean up any misalignments in genomic sequences, preparing them for further analysis. And the analysis is now completed successfully. To allow us to demonstrate both hybrid and cross-cloud workload mobility, we've enabled access to two public clouds, Amazon Web Services and Google Cloud Platform. Leveraging Elastifile's Cloud Connect capability, we've already established connections to the object stores in these two environments, but as you can see, the object stores are currently empty. Next, we're going to leverage Cloud Connect to tier data from our on-premises file system into object storage on our two cloud environments. In this demonstration, our on-premises file system is an Elastifile file system, but Cloud Connect can efficiently transfer data from any file system into object format while retaining the file and directory hierarchy information as well as versioning information. So let's go ahead and check in our files. First, we're going to perform a check-in into AWS Object Storage. Check-in completes successfully, and next we're going to perform a check-in into Google Cloud Object Storage. It's worth noting that Cloud Connect deduplicates and compresses data before transfer and only ships differences after the initial sync, thus enabling cost-effective, efficient hybrid cloud connectivity. Now we see the check-in to Google Cloud has also completed successfully. When we return to the Cloud Connect UI, we can now see the 2 GB of data have been checked into object storage within each of our public clouds. Here in the Google Cloud UI, you can see the associated objects that we've created. Again, these objects reflect the files and directories, including the hierarchy information from our file system. Next, to support our genomics workload in the cloud, we're going to deploy the Elastifile Cloud File System on AWS. For this first deployment, we're going to leverage the Elastifile Management Console to perform a quick and easy installation. First, we'll specify a few configuration details, such as the number of node failures to tolerate, networking configuration information, etc. Then we'll specify the desired capacity for our cluster. In this case, we're specifying 9.6 terabytes, which will trigger the creation of 3 Elastifile storage nodes. Finally, to expose an externally accessible file system, we'll create a data container specifying access permissions and the desired policies, such as compression, deduplication, capacity quotas, etc. To verify that our infrastructure has been deployed successfully, we can navigate to the AWS UI. And there we can see the 3 new active instances that have been spun up as a result of our configuration and deployment. In the Elastifile UI, we can see that the file system is currently empty. To populate our file system with the data needed for our genomic analysis, we're going to check out those files from our AWS object store. With the checkout done, data is now populated within our AWS file system. Now, with the data loaded and exposed to the application via Elastifile's POSIX-compliant file system, we can now run our genomic workload in the cloud. Here we see the necessary files within the Elastifile file system on AWS. And next, we're going to execute the GATK genomic analysis job. And the job completes successfully. With that, we've now demonstrated the dynamic ability to shift and burst a workload across a hybrid cloud. In many cases, however, multi-cloud architectures can be beneficial, whether to dynamically leverage cost differences between cloud vendors, or to take advantage of features that may be specific to a given cloud vendor. To demonstrate this flexibility, we'll now run our workload on a different cloud, this time the Google Cloud Platform. And to switch things up a bit, this time we're going to execute a fully automated deployment using Terraform and Elastifile's REST APIs. Here you can see the Terraform plan defining our deployment. This plan captures all the configuration settings and activities that are needed to deploy our environment. And next we're going to kick off the Terraform process that executes the automated deployment. This deployment includes the cluster creation and the setup and configuration of a data container. When the Terraform process completes, our GCP-based Elastifile file system is now ready for use. And here we can see that 3 new Elastifile instances corresponding to our newly created cluster have been successfully created within GCP. And to load the files necessary for our genomic analysis, we're going to perform a checkout from our GCP object store. And with the checkout complete, our Elastifile file system is now ready to support active data processing by the genomic application on Google Cloud. Here we can see that the necessary genomic files are now visible within our Elastifile file system on GCP. So we're going to execute the GATK analysis job. The job completes successfully. Now I should also note that the results of any analyses performed within our on-cloud infrastructure, for example any file creations or modifications, those results can be checked back into our object storage, just as the files were initially checked into object storage from our on-premises infrastructure. By enabling this check-in to cost-effective object storage, Elastifile enables users to not only dynamically spin up, but also dynamically spin down the in-cloud file system infrastructure, thereby minimizing cloud costs. And finally, if those results are needed on-premises, cloud egress charges can be minimized by shipping back only the data corresponding to those results. This can be done as a batch process leveraging Elastifile's Cloud Connect capability, or if the on-premises file system is an Elastifile file system, it can be done instantaneously by leveraging Elastifile's asynchronous replication service. So now that our work is completed, we're going to demonstrate the ability to dynamically tear down our cloud-based file system infrastructure. To remove our infrastructure quickly, we will again leverage Terraform automation and Elastifile's REST APIs. As the Terraform process executes, the cloud instances and the storage associated with our cloud file systems are removed, ensuring that cloud infrastructure costs are incurred only when the cloud-based infrastructure is truly needed. And here in the GCP UI, we can see that our ECFS cluster instances are in the process of spinning down. And with the Terraform process complete, our on-cloud infrastructure has been dynamically removed, thus preventing the accrual of any unnecessary cloud costs. And with that, we've demonstrated how Elastifile delivers cost-effective, real-world multi-cloud architectures, enabling dynamic workflow mobility from on-premises to cloud and between clouds. Thank you.